it works, it's less work than me when I do the discussion section. That's why. Like, oh, like, here's all of it. Our introduction. Because I know that all the doctoral work, I'm going to take away all the advanced classes during that time, and no one wants to teach the introduction class.
I know that everyone wants to intro class. Slide in a 5 minute intro class.
CSC 30. He said there's like 10 CA. The other one should be like 10 or more. CSC 30. CSC 20s are 4. I need 2 doctorals, 2 masters instead. Or 4 TAs.
Shall we get started? Everyone, yeah. So just actually, so a few announcements. We're releasing the assignment 3 soon today. I hope everything went well with the assignment 2. I had a few opinions that it was easier than assignment 1. Did everyone feel like that, or? Yeah, and. We'll also release some grades with the grades for assignment 1 also soon. We're checking with the graders. We actually already spoke to my TA, so we already have provisional grades for assignment 1. We have to double check a few things and then we'll release them soon. So yeah, sounds good. So last time we were talking about the naive Bayes classifier. Does everyone remember what was the key assumption we had to make in the naive Bayes classifier? So it's not even here on the slide. What was the key assumption the naive Bayes classifier was making? Independence, yes. Between what and what? Yeah. So we assumed that the likelihoods of observing our x's given the label are independent. So the whole p of x given y was factorizing into p of x1 given y, p of x2 given y, and so on. So that was the key assumption we were making here. So this is how this is showed here. You see this product here over all these x's is this is the key assumption in the naive Bayes classifier. So, and if you remember, we went through this example and showed how it can lead to predictions using the posterior, and sometimes even though some examples in the training set were of the opposite sign, of the opposite label, and this is because of the independence assumption that it was making. And we said how naive Bayes is a generative model. It's not a discriminative model because it can generate data, new data points. And we went and we briefly showed how if you write it like this, it starts looking. So if you write it as the prediction as a fraction over the posterior with y equals 1 over y equals 0, and the same with these likelihoods given y equals 1 and y equals 0, and you compare if this is greater than 1. So this means that the top part is greater than the bottom part. It starts looking awfully similar to a logistic regression. So it looks really similar to logistic regression. So then if we rewrite these, we use the trick from logistic regression where we write these as pi, this parameter p of xi equals 1 given yy equals 1 as pi, and the same thing for x1 equals 1 and y1 equals 0 as qi. We rewrite it with this trick, the same fraction. So when xi equals 1, it will just be pi. When xi equals 0, this will be 0, so this will be this term, 1 minus pi. And I'll let you go into more detail at home on this. I won't go I won't explain everything here, but essentially, we end up with this form now. We rewrite this top part with this trick, and then we take the log, and we get this expression where we all our products turn into sums. So we get and we notice how this is a constant with respect to x's. So this is a c, and the right side is a weight w that does not depend on x. So we realize this is just the prediction is just a weighted sum of our data points, x's. And we just check if the with this weighted sum plus the constant is greater than 0. And what happens when pi equals qi, when the probabilities are equal? Well, what happens is that this weight becomes 0, because the weight is simply this fraction, this parenthesis here. So this term will be equal to this term when pi equals qi. So then it means that feature does not matter for the prediction. That's what it means. So the features become irrelevant when the weights are 0. And finally, again, I'll let you go through this at home, but essentially, if we rewrite this, the posterior of y equals 1 given x as this, and we use the previous form we just derived from here, c plus wi xi, we see how this becomes exactly the form of a logistic function. So this, so essentially, the logistic function is inherent in the naive Bayes classifier. This is how in the posterior when we're talking about binary labels in particular. So this is the key takeaway sort of here, that this has the form of a logistic function. Any questions? Okay. I'll show you here a really interesting example of how we can use naive Bayes to do text classification. So naive Bayes has been used a lot for text classification in the past, and it makes more sense than, for example, running it on images, because there's less independence between words. The words will be our observations. And for example, imagine you have documents, large documents, and you want to classify the documents. Oh, this is a law document, this is a feed on Facebook, this is something else, this is an article, scientific article, and so on. And the words are our observations. So there's more independence assumptions in those, which makes it suitable for naive Bayes than, for example, applying it on images. Applying it on images doesn't work that well, because the pixels are highly correlated. The nearby pixels are really highly correlated. If you have a pixel that is red, it's highly likely that the nearby pixel will also be red, color red, I mean. So, but for words and text, it gets better. So if you assume that V is our vocabulary, all the words in the documents, and then if we assume that each document belongs to a class, so again, this could be a law document, or again, a feed on a social media website, all kinds of things, or other document, for example, in a different category, like a math document and so on. And for each word W in the vocabulary, we denote by this to be the number of times W occurs in the set of documents that belong to that particular class. So these are, like, for example, docs Y, all the law documents, or all the documents in a particular class Y. So what we do is that we set the likelihood of observing a particular word given the class to be the number of words, the number of occurrences of this word in the set of documents of class Y. Forget about this one for now, and you divide by the total number of occurrences of all the words in the documents. So this is sum over all the words of the same thing. So essentially we count the proportionally how many words of this type are in this class compared to all the words in the vocabulary. Now we do something a bit more this won't be enough. We have to do something a bit more complex. Essentially, if you just do this, if you don't add this plus one and so on, don't do this smoothing, what will happen is that some words in the vocabulary, you might never find them. For example, you might never find a certain kinds of words in a law document, for example. Talking about, let's say, equations, so like, let's say, Bayes theorem, for example. So the words, for example, Bayes theorem, you might never find them in a law document. So then what you do is that you do this smoothing where you add plus one and you divide by, then because you add plus one for each of these occurrences for all the words, then you divide by total number of vocabulary as well. And this ensures that these will never be negative, will never be zero. These fractions will never be zero. Because you can have, if you have no occurrence of a particular word, this will be zero, basically, this likelihood. And we don't want that, because if this is zero, then the whole, this whole expression will become zero later on, and that will be our posterior. So then it won't enable the inference. So that's why we do this smoothing operation. We add plus one, and then also add the total, the number of elements in V. So then we predicted on a new document X with class Y by maximizing this expression, and this is the prior over the label times the individual product over each word given a label. What does this equal to? What is this expression? This whole thing with Bayes theorem. Any ideas? What does it look like? Sorry? No, that fraction before is how we express this likelihood, what we're talking about here on the slide. But what is this whole thing? What is what if you apply by Bayes rule? What would this be equal to? This is the prior, and this is the likelihood term. What will this give us? The posterior probability, yes. Of what? The posterior of what? Yes. We have to find the posterior over the label. We want to find what is the label for this document X. This is the task. So we have to find a posterior. So we're getting a posterior over Y, over the label Y that we want to predict. So this will be equal to P of Y given X. The posterior over the label given this document. Yes.
Shouldn't there be a normalization term?
Yes, there should be. But generally, that's very easy to deal with. So first of all, that normalization term is generally quite hard to compute in many cases, but also you can it's fine. You can even if you don't have it, you can just take the maximum over and that will still work. Because that normalization term is a constant with respect to Y, so it does not depend on Y. So that's why. Okay. So it makes sense that we want to predict the label Y. So that's why we're computing. This will give us a posterior over Y given X. I won't do this. So let's move on. So, nearest neighbor classifier. So one of the things we'll start talking about today is k nearest neighbors, and actually we should finish this, and we're also going to start talking about decision trees. So the two really important classifiers and methods in machine learning. So this one is actually it's very intuitive, very important at the same time to understand. People, it's still heavily used in many cases. For example, the group of the professor who was teaching this course last year, they published a paper recently on using k nearest neighbors. So it's very it's still very popular. And we're also going to talk about decision trees soon. So after we finish this, so has anyone used k nearest neighbors so far? You have used it? Yeah. Nice. Anyone else? No. Well, we'll see. It's actually it's quite intuitive to understand it, and again, if you have any questions, do interrupt me. So far we spoke about, for example, different types of methods. Some models are generative, some models are discriminative, and so on. Another type of categories between these models is what's called parametric and non-parametric. So parametric methods are methods that have a fixed number of parameters, and they are generally very well defined, and we're trying to optimize them. So for example, linear regression has for example, like, ax plus b equals 0. We're trying to optimize a and b. So those are the two parameters we optimize, and so that's a parametric model. And whereas some other types of methods are non-parametric because they do not fit a parameterized models. And for example, nearest neighbor is a type of classifier that does not, that technically doesn't have parameters. Although it's, you can still say even here that it does have some parameters, but generally people refer to them as non-parametric. There's other types of methods as well, density estimation methods, for example. Like for example, like some kind of like a parse and window classifiers. Those are also non-parametric, and many others. Like for example, people talk about the Gaussian processes being non-parametric because, and essentially one of the key things that they use the data as parameters. The data is used directly as the parameters of the model. So we don't have sometimes explicit parameters in these. So let's see. So let's imagine we have this training data here. So these two features, we have these two classes and these data points. What should be the label of the red point? Like you could eyeball this and you can tell that, oh, it's clear that it's most likely it's a black class instead of a blue. So this is kind of and the idea is because you kind of like this is in the neighborhood of these other points. So this is very close to the black ones and much further away from the blue ones, and that's why it is a black point, because it's in the neighborhood. It's very close. So the neighbors of the red point are all black.
You can say, like, I'm going to look at this many neighbors and
Yes,
look, like,
yes.
the closest ones.
Exactly. So the idea is exactly that. We look at the neighbors and we say, oh, the neighbors are all black, therefore this should be black as well. It's very simple. As long as you have points in the neighborhood, it will work quite well. So this is the key idea. So then, we have a set of training examples, x's and y's. So x's are the data and the features, y's are the labels, and this is the many training points. And to predict on a new x, we find the closest data points to x, and then predict with a label. Sorry, I'm about to sneeze. So it's not just a simple table lookup, because we have to also compute distances between the neighboring points. We have to find the neighbors, and to find the neighbors, we have to compute distances between all the points. But it's something. It's very close. Once we compute distances, and then we find which are the neighbors, are the closest to the neighbors. So in the case of something called one nearest neighbor classification, we simply look at the closest neighbor, at the single closest neighbor to the red point, for example. So to the closest neighbor is the black. So then we simply say the label of this point is a black. It's in that class. But sometimes what might happen is that if you take this a single neighbor, that might not be robust enough, because you might have noise, you might have other problems. So what might be sometimes more important is to look at more neighbors. And this is where, like, for example, k comes. So then if k equals 3, then you're looking at the 3 closest neighbors. And you make the classification based on those 3. So in this case, if you take k equals 3, then these are the 3 closest neighbors. And then we do majority voting. We do like a voting system where we say, oh, there's now 2 points which are blue and only 1 point which is black. Therefore, we're going to set the final label to be a blue one because there's more. Yeah.
Would you also possibly weight the neighbors? Like this black point is really, really close to the red point.
Yeah,
so
yeah. You're ahead. Yeah. So you can. I'll talk about that in a second. So you can weight this distance by the distance. We can weight the vote by the distance and other things as well. So you can do that. But the idea is now, if we take a larger k, then this will hopefully be more robust. For example, in case of noise, for example. So. And you see the choice of k can change the label. Initially, when we had k equals 1, this will be a black point, but now when we have k equals 3, this changes the label to blue. So this is, for example, the implementation of k and n. It's actually super simple. So if you look here, what we start with is the data set, the point. No, the k is the number of neighbors k that you take into account, and the point x. So, and first of all, the first thing we do in the pre-processing step here in the first part is to compute distances between the points. This is what we do in the first 4 lines. We compute distances and we store them. Store distances between from our query point to all the other points in the training set, and then we sort the distances. We put the lowest ones first, and then for all these k's, what we do is that we compute a distance. We retrieve the distances that we already computed, and we take the first k distances, and then we sum the labels basically of those points. And we can do this sum because the labels y are binary. The y is a is a 0 or 1. So then that's why we can do it like this. Sorry, a -1 or +1. So again, we just pre-compute distances, and then we will retrieve the k closest ones, and we compute the vote, the final vote. And yes, indeed, the distance metric is important. So, for example, let's take an example with expensive houses to understand this better, to understand why the distance metric is important. So imagine you have a house and you're trying to predict the price of it, for example, based on several features. And imagine the features you use is the number of bedrooms from 1 to 5, the lot size in acres from this to that, and also the house in square feet. So from 1,000 to 200 to 3,000 plus. So if you do it like this, if you just keep, for example, these 3 features, the distance in square feet will dominate the computation because these are very large numbers, and these will dominate the computation of the nearest neighbors. Whereas these other features will not count too much whether the number of bedrooms is 1 or 3 or 4 or 5. So this is a problem. The problem is that some features can dominate the prediction. And what we have to do is to normalize. We have to normalize and make them have the same standard deviation and so on. Some other times maybe we have some irrelative attributes, for example, that can be problematic. Like, for example, if we know how far away was the owner born, for example, this is completely irrelevant to the prediction problem, and it could add noise and lead to overfitting. And also, correlated attributes are also bad. Why would they be bad? Why would correlated attributes be bad?
You may kind of overweight if they both kind of are signaling the same kind of
Yeah.
information, and then
Yeah.
they're both
Yeah,
confident,
yeah,
giving it too
yeah.
much weight towards that particular data, right?
Exactly. So they could together, when for example, if 20 features correlate with each other, then altogether they could end up dominating. Like for example, doing exactly like this feature here, which is a very high magnitude. So all together, all those quality features could end up dominating the prediction task.
It almost feels like these three would correlate with each other.
The-
Number of bedrooms, size of the lot, square feet.
Yes, they would correlate. They would correlate. Yes.
So this would be a bad set of features.
On many regards, including correlation, including scale. I think the main problem here is scale. And then even if you normalize the scale, you still have you're left with some correlations. And to remove yes.
Is highly correlated attributes bad across all machine learning models or just the k-nearest neighbors?
That's a very good question. Are highly correlated attributes bad across all machine learning models or just KNN? Generally, it's a complex answer to give. Generally, some models will not, some ML models will not be able to deal with the correlation that well, whereas others, more sophisticated ones, can deal with the correlation. It's a matter of the ability of the model to capture the correlation. For example, I think there's a class of models called Gaussian processes that we will not cover in the class. But essentially, what happens is that you end up fitting high-dimensional Gaussian distributions to the data. And those Gaussian distributions will require a covariance matrix. And you can have that covariance matrix to be estimated from the data, so they can capture the correlations. Or sometimes some people fix it a priori to a diagonal matrix, just to make the inference faster. And if you fix the diagonal matrix, for example, to an identity to a diagonal matrix, then you will not capture any correlations between the features because it's completely it's assuming they're completely independent. So then what happens is that you assume the diagonal matrix is fixed, the covariance matrix is fixed, but the data has correlations. So you will not be able to capture them, and it might fail if it has correlations, if it has strong correlations. That's an example I can give you. So, but with the same model, you can try to estimate the covariance. That increases a bit the complexity, and increases a lot the complexity because it's a huge covariance matrix. But then you start being able to capture correlations. And with the same Gaussian process model, you can do that, but at the expense of having much larger parameters and making the inference problem much harder. Yeah, a question.
In the previous slide, we had a pseudocode.
This one, yeah.
So in this, what happens if the value of y is 0?
What happens when y is 0?
In the output, like we keep on adding the labels.
Here.
Yeah, so what if the final value of y turns out to be 0?
There has to be at least one k that is added.
Does k have to be odd every time?
Sorry, does k have to be?
Odd every time? Should it be odd number every time?
Oh, because we can add a -1 and a +1. Yeah, I see what you mean.
I guess you'd have to add something to handle it if it wasn't odd.
Yeah. So what that's the case. What happens when you have the same number of points on that are both with two classes? So the voting would be split, would be equal. The final, So you have to take a decision either way. In that case, so it's not complete. Yeah, this algorithm is kind of, you would need to have a special case for when y equals 0. That makes Yeah, so that's a good observation. Very good observation. Yeah. It's more to give you an idea. It's like a pseudocode, but it's not. You have to break it somehow. This will be an even vote, 50. It can be 50-50. Any other questions? Okay. So we have this. Let's do a short class exercise. Let's take this. We have a problem here. So we have. Let me explain this. So we have a point x that is in 0, 1, and you have to determine its class. So basically, the y equals 1 if x1 is greater than 0.3. So if this point x1 is greater than 0.3, so that this is a classifier we have. And now consider predicting on 0, 0 given this data. So given you have two data points, 0, 1 and x2, this is labeled 0, 0, 5 and x2 prime is labeled 1. And we draw random samples x2 and x2 prime from 0, 1. So the question is, what is the probability of making a mistake with the one in nearest neighbor classifier here? So what is happening, I'll draw a short diagram, is that we have two features, x1 and x2. And we have two data points, 0, 1, comma x2. So that's, let's say here 0, 1, 0.1. And we have a line, x2. So somewhere on this line lies one data point. And somewhere at 0.5 on this line lies the second one. So here lies one data point, let's say here. And somewhere on this line lies another one. And we have to compute a distance from the origin to these points. So what's the probability of, and one of them, this one on, so on 0, 1 has label 0, this one has label 1. Now 0, 0 has to have label 0, right?
It should be labeled 0.
Yeah, 0, 0 has to be labeled 0, so this has to be y equals 0. So what's the probability that we make a mistake on this? I'll give a minute and a half, so we'll take a pen and paper and do it now. You have the problem still there. it? Anyone? Good. Actually, I might not need this. Okay, shall we do it? So what's the probability of making a mistake? So the probability of making a mistake here is the probability on 0, 0, on data point 0, 0, is the probability of predicting 1 on 0, 0. Yeah, so that's when we make a mistake, if we predict a 1 for that data point. And the probability of predicting 1 is, so we will only predict 1. Let me put this to the side. Only if this data point with label 1 is closer than this other data point. Remember, these are sampled from on these lines, these points. So this point will have to be closer than this other point. This distance has to be shorter. So is the probability of this point y equals 1 closer than the y equals 0 point. So that's the probability that the distance, that this distance is shorter than this distance. So that's this distance is equal to so it's 0, 5, x2, 0, 0. This distance is less than distance between 0, 1 is x2 prime and 0, 0. Yeah, so this distance has to be shorter than this other one in order to make a mistake. So if you write out the distances, and we can keep the squares, this will be the probability that 0.5 squared plus x2 squared is smaller than, so this 0.5 to 0 is 0.5 squared, x2 squared, then is smaller than 0.1 squared plus x2 squared. So this is when we make a mistake, if this distance is smaller than this other distance. And the first step we do, so now if we say that this is equal to p of x2, so we just move 0.5 to the other side. So we say this is a probability of x2 smaller than 0.5 squared is minus 0.5 squared plus 0.1 squared plus x2 squared. So this has a minus here. It's more than minus 0.5. But remember now, these points, x2 and x1, are sampled from 0, 1, from the 0, 1 set. So I'm adding here, so x.
You wrote x sub 2 on both sides of the inequality. Should one of them be x sub 1?
Say it again.
The probability of, yeah, so shouldn't on the right side it be x sub 1? Okay.
Should be what? Sorry, on the other side.
So the other x, is that also x sub 2? Are those the same?
Yeah, it's x2 and x2 prime.
Okay.
They are. That's how
Okay.
in the exercise. So I'm missing a prime somewhere here. The right side has a prime. Yeah. Okay. Yeah. Is it good now? So if we know that x2 and x2 prime, they're both in 0, 1, then we write this out as an integral. So this is going to be equal to an integral. So x2, we turn it to an x. So x equals 0 to 1 of p of x. But p of x will be equal to 1. Remember, because this is a uniform distribution times this the probability of written like this. So times p of x two squared less than minus 0.5 squared plus 0.1 squared plus x2 prime squared dx. So, and I have and one of these x's will turn into an x into this x. So I think this one gets fixed. Yes. So this one. So what we did here is that we fixed an x. We fixed x2 prime to a particular value, and then we wrote this as an integral from x equals 0 to 1 of p of x, which is equal to 1 times that. So and then the whole thing is the idea is afterwards you do the same thing here. Write this as an integral as well. You also fix the x and write this as an integral, and you can sort of like use a calculator to compute the value. But it's not. It won't give a closed form solution. It won't give like an analytical closed form solution. Like you have to use a calculator to compute. But that's sort of the idea. The idea is you express these distances and then you reach this form, and then you separate one variable from the others. Any questions? Yeah.
Could you also solve this one in a more intuitive way where you just plug in all the combinations for x2 and x2 prime and then just take like a proportion of what?
Yes, you can. Yeah, that's a Monte Carlo approach, and you can do that. Yeah, you can get a very close solution to that, like that. Yeah. You can solve it like that with the Monte Carlo approach. You can do this and use a calculator. You can, yeah. There might be some other ways to do it. Okay, shall we move on? Let me see. So what we get if we solve this with a calculator, we would get a value of 27% of making a mistake. So 27% of the times, this point here can be closer than this other point. So even with the nearest neighbors, so the whole thing, what this is saying is that even with the nearest neighbor classifier, we would make a mistake. For example, 27% of the times in this particular case. So it's not always like correct, and yeah. Let me try to remove that. So some tricks we can use to make this learning better, and make sure we have less mistakes, and even fix some of these problems we were talking about before with how some features can dominate or be correlated. What we can do is that we can normalize the attributes first of all to a mean 0 and variance 1. If we normalize this, then we can this way ensure that, for example, not some features will dominate other features. And the other thing we can do is, as a colleague suggested, is to actually weight these distances. So use some weights, and only use the features that are actually important. And one way we can use weights, for example, is to use something called mutual information, which we're not introducing yet. We'll talk about it very soon, actually. But this mutual information intuitively measures the amount of information that is shared across these two random variables, across the x and the y. So if these variables have a large mutual information, that means that means that this particular feature xj is informative for the label. So then we would weight it higher than some other feature which is irrelevant. So this is how we can get rid of irrelevant features using this weighting based on mutual information. And there's even some other sort of methods by using, for example, Mahalanobis distance, where we have a distance form. So this is x minus x prime squared, but we have also a covariance in the middle, which is inverted. And this covariance essentially can model correlations between features, between feature I and feature j. So this is for dealing with correlation among features. And then when I was telling you the example of Gaussian processes, for example, this is the form you will have also in a Gaussian process. You'll have a covariance matrix here, right in the middle between these two vectors. One problem that we encounter with nearest neighbors classifiers is the curse of dimensionality, and we spoke a bit about it some lectures ago. So as the number of attributes d goes up, so does the volume. So d is the number of dimensions we have in our training set. So x's have a number of dimensions, d, and as the number of d gets really high, then this explodes in dimensionality. So one way to illustrate this is, for example, if you consider we have 1,000 training points in this space in 0, 1 to the power of d. So this is a unit interval, but in d dimensions. Sorry. Where does each point predict? So if you have d equals 1, we have basically for 1,000 training points, we have on average 0.001 the width of each segment, basically the distance between each point will be on average 0.001. When we go into higher dimensions, the area per point would be still the same, 0.001, but the length of a side would be around 0.032. So it gets much larger than before. And here, by the length of a side, what we mean is something very close to the distance between the points. It's something like if you have if you're in 2 dimensions, for example, and if you have 4 points, by area we mean the whole thing. So per point you have 1/4 area, but the length is this. This is what I mean by length. So this is length. So this length would still be a half, will not be a quarter. And when you go to higher dimensions, to d equals 10, this length would be around 0.5. So basically, on average, the points could be around 0.5 apart from each other in when d equals 10. Even though we have 1,000 training points, 1,000. So you see, as we increase the number of dimensions, we need a lot more data points to cover the space and to cover the volume in particular, the hyper volume. So this is what the curse of dimensionality, is, and that means, nearly stable classifiers can have this problem, and we need higher dimensions. What is a way to reduce dimensionality? Yeah, PCA. Yes, we can apply PCA beforehand to reduce dimensionality and fix some of these problems from this. So and then run a nearest neighbor classifier. Yeah. There's also something. Actually, why don't we take a break and then we continue after this? Let's take a 7-8 minute break and we'll continue right after.
Yeah. like an extra thing, but I just can't hang out that long.
Yeah.
I want to do the studying.
Yeah.
But Thursday definitely.
There.
So there's the first year.
Yeah, not Friday.
You
Friday,
use
Friday, I have
this
discussion
discussion
session.
The class I'm taking for the head of midterm on Thursday, and I've got to do something.
If you get
I gotta figure out how to like
if you get the first year, if you get just
make a rubric and
if you get this aspect, this one,
Structure
after
using the river.
this one,
Oh, I've got to make a rubric for this one.
you can use the
No, I have to do it on
first
Crazy, but I just don't know how to do it on
If you get the
Facebook.
air, the reading or the pro, you have to use the second one.
You have to, you have to make it. You use Facebook as a student.
Yeah, is because the other one you like.
I'm doing it as a TA, so I'm not using it as a student. I'm using it as a TA. I've got to make a rubric. It doesn't seem like it's hard or anything, but I don't think it'll take that long. I just got to watch like a couple of tutorial videos.
The MacBook Pro.
By the time you get on the meeting, like as TA, you get to look on the quiz. I try to be careful with the TA meeting. I said that right.
Yeah.
So I said, a lot of students just they confused on this example. I looked at her quiz and enough to create that example, and then during her lecture, I watched it a little bit. But then explain more, show more. I guess I have to explain this. I guess I have to explain it more.
Yeah. But all the first
Because this is
TA,
M1 Pro.
classic move.
M2 Pro is not
It's how it goes sometimes. This is what these are there for though, that I can't put more details on.
Kind of like this classic mood.
but I can give you a good deal.
You should PS more.
If you want.
Well, that's what the straight stuff is probably going to be about here.
Yeah, so
You should PS more.
double the two more GPU cores,
Yeah.
double the storage.
You can.
It's
I don't know, but yeah.
400.
So when you go select TAs for the winter quarter?
Oh, I won't select them. It will be, I think, late December or early January.
You got to wait for all
Like,
the.
and I won't select them. It'll be Roberto.
What? Roboto?
Roberto Manducci. He's another professor in the department. He was like he does the allocation of TAs for all the courses.
Oh, what? He does everything?
Yeah.
No, wait, so he's a department chair.
He's not a chair, no,
No?
no.
He's just there to assign the TAs.
But he assigns the TAs. Yes.
Oh.
Yes.
Okay. I did not know that.
They've got to wait for it. Not, I mean,
And it's not now. It's
the
yeah.
applications are still open right now.
Oh,
The
yeah.
applications close on the 31st.
Oh, yeah.
So it's going to be a while after that.
Yeah.
I checked this on Mac.
I did my application. I wanted to take his class.
I'll get it. Oh, I'll try and do it today.
He has a CSC 30.
Oh, yeah. But which one is that? The CSC 30?
Sorry.
Which class is CSC 30?
Programming abstractions in Python.
Oh, that's a fun class.
Yeah.
I take for 101 most of the time.
Yeah.
It's also a thing. But that's mostly just code.
Yeah.
Students come in and be like, have a bug. How do
Yeah.
I fix it? Like, well,
Yeah.
what have you written? Too many students, they need to learn, compile the code a little bit at a time still. But that's what I'm telling them most of the time. They're like, I have this code, does it work? I don't know. Have you run it? They're like, no, I haven't run it. I was like, well, I don't know if it works.
Yeah.
And then they're like, run it. And then they run it. I'm like, it's not working. I'm like, okay. And they're like, why is it not working? I'm like, oh, well, I don't know. You have all this new code to look at. You can't
Yeah.
But
When did you TA for it?
I've been taking, so I came for 101 the winter and
Okay. Shall we start? So So we're talking about the curse of dimensionality and certain tricks we can do to make learning easier for k nearest neighbors and sort of like make less mistakes. Another thing we can do is that when you compute a distance function in k nearest neighbors, we can use any of these distance norms that we want. Any of these would work. So, and you've seen these before. For example, we can use an L2 distance, an L1 distance, or even like a max norm. And these circles represent all the points. A circle are all the points which are of equal distance to the origin. So in this particular norm, these points are all of equal distance to the origin. So these points will have like low distance. This will be high distance. And whereas in L1 distance, these are all the points that are of the same distance to this. So these are all like contours of this like landscape, or level sets. Some people call them level sets or contours. So these are all like points with the same value in these distances. So you see the differences of how they look like, and this is an example of. Let me come so I can see it from here. So this is an example of a classification with nearest neighbors on this data set on 3 points, three x's, 3 circles with the L2 distance, and look at the difference between the L2 distance boundaries and the L1 distance boundaries. Look how they're actually different from each other. You have a corner here, a single corner, whereas here it becomes a more like a right angle. And so the choice of the distance will affect the boundaries, the final boundaries of the classifier. And this is the case for not only for KNN, but for any other ML model. Like we were talking about regularization early on when we did least squares, and we can do a regularization with an L1 norm or an L2 norm, and the same thing, that will also give us a different solution.
Is the way you would pick the distance be like compare performance on the test set or something, and then pick the best one? Or
You can do that. So he's saying, can you choose the norm based on a performance on a test set? And the answer is yes, you can do that. Yes, of course you will do that on a validation set, but then on the test set you can try different ones, and of course if you try many of them, you might have some overfitting effect even there. Imagine you have 100 norms that you try, because there's an infinite number of such norms, and then some of them you might even overfit on a particular test set. But yes, you can choose them based on a test set or validation set performance. This is a different, for example, if you change the boundaries, if you change the number of k neighbors that you choose, this is how the boundaries change. So with k equals 1 versus k equals 3. Notice how when k equals 3, the boundaries become a bit more smooth, like you have more like almost straight lines. You don't have all these like angles that much anymore. Having even noise can cause problems with k nearest neighbors. Imagine you have a data point, a label here that is in between these x's, so this will create its own little neighborhood with our KNN classifier. In the case of k equals 1 here, this is an example of k equals 1. So having noise can cause problems. And however, it has been shown that if you have a lot of data, like in the limit of infinite data, and as well as a large k, almost infinite k, it has been shown that KNN is what is called Bayes optimal. It gives you an optimal performance on the prediction problem in this limit, and this is a result that has been known for a very long time. And I won't formally define what Bayes optimal means. It's something about it's a property that shows that the classifier is optimal in a particular setting. When it's talking about the risk of the classifier, and we won't cover that, but it is an optimal classifier in the limit of as data goes to infinity, and it does have hyperparameters. So k is a hyperparameter that we can tune to tune the complexity of the hypothesis space. So So the k does control the hypothesis. So for example, if k equals 1, every training example has its own little neighborhood. Whereas for k equals n, the entire feature space is one neighborhood. So n here means all the data points in the training set. So the higher that we increase the k, the more smoother generally the boundaries will be. Whereas with a low k, this will be more sharp or jagged. So higher k yields smoother decision boundaries. So how could you set k in practice? Could you do the same thing our colleague suggested? How do we choose k in practice?
Hopefully we want to be able to make an observation about the distances. So if we say on average we get a group of points that are like this distance apart, and then there tends to be some blank space, and then another group of points, right? So I guess if we have like one bucket, and then we say everything with here is within the, like an x distance, and then an x plus y distance away is about another bucket, you'd probably want to average the amount of points that are in each bucket and use that many neighbors. So you just don't want to be looking too far away, right? If k is too high, you may end up looking at neighbors that aren't very neighborly. They could be pretty far, right?
Yeah. One idea is to do cross-validation, or first of all evaluate on a test set and then do cross-validation. So we can choose k, for example, by having a separate test set or validation set, and then validating on that, making predictions on a separate data set. And then we can do cross-validation. We try different folds and so on. So that's, for example, one way. And we try multiple k's. We compute the performance on these validation sets or test sets, and then we see which k gives us the best performance. So that's one way we could choose k in practice. And there's another way to do this. So instead of choosing a k nearest neighbors, and something else we can do is to instead take an epsilon ball and then only take so we take a fixed distance, for example, a distance of 2 or 5 and so on. We set a fixed epsilon, and then we take all the x's that are within that distance, and this helps us solve the problem of when, for example, some regions of the space are very densely populated, so they are dense, and some other regions are sparse and they have not many training points. And in this case, the choice of k would ideally we want different sort of like k's for different regions. But this way we can solve this by just taking an epsilon ball instead. So in some regions of space we'll have a few data points lying. So we have a data point x, and we just take an epsilon ball like a ball around it of length epsilon, and then in some regions of space we might have a few data points, and in other regions we'll have a lot, for example, a lot of points. So we could vary how many points we actually have inside this epsilon ball, but then we still do majority voting again within this region. So what is the value of k in this variation? Yeah?
Doesn't it change based on every data point?
It changes, yes. So we don't have any more value of k. It's, yeah. What do we have instead? What's the hyperparameter we have now? Epsilon, yes. So epsilon we have to fix a priori, which is this distance. Yes.
What if no point is within the epsilon?
Yeah. Yeah, that could happen. Yeah. Again, you have to have a special case in that case. Have a special, have a corner case that you deal with. If that happens, then you still fall back to k nearest neighbors, for example. You can do that.
So can't we like keep on increasing epsilon until we find a point?
Yeah, there's another option. Yeah, that's another option. Generally, though, you would run this with a fixed epsilon, but yeah, unless you have a corner case like that, in which case you can try all these variations. Yeah. Okay, so let's start with decision trees, and we'll continue next time. But I wanted to also do. So we're going to start by talking about this new type of classifier called decision trees, and we'll continue next hour. Decision trees are a very popular machine learning model, very popular. They're they're generally very robust. They're interpretable. You can interpret what they learned. We have some very nice algorithms that can learn decision trees. We can see even later, we can do like, people even do random forests, which are basically putting many of these trees together and using we can combine it with other techniques such as boosting. We'll see later in the course at the end, in the final weeks, how we do boosting, and all kinds of, yeah. But this is sort of like, we're sort of like covering the very fundamentals of decision trees. And we'll see later on how we can, make these even more interesting. A decision tree is basically, let me again try to take that out. I cannot remove that. Okay, I guess we'll keep it like that for now. So decision trees are basically a tree that you learn, and you ask several questions. Are you, for example, hungry? If you're not hungry, then go to sleep. If you're hungry, you ask another question. For example, do you have $50? No, you go to fast food. Yes, you go to restaurant. So you have to take an action or make a decision or make a prediction, and you ask a series of questions that takes you down on a tree branch. And at the end, you reach a leaf node, and this leaf represents a prediction, a label for our data point, or an action that you take. So, the reason why we do that is because we have data that comes from many representations, and we sort of want to compress it in such a way that then we can, build some boundaries and classify. So, for example, imagine you have these shapes that are one class, the plus class, and these other shapes are minus. So we can make a prediction, for example, as follows with a tree. So, for example, we check the color. If the color is blue, let me start with red. If the color is red, then we know all the reds are in this class, so we can put a plus. If the color is blue, then we check the shape. Is it a triangle? If it's a triangle here, then it's a minus. If it's a square, it's a plus. If it's circular, it's also plus. So we ask a series of questions, and then at the end we make a prediction. And making the prediction is easy if we have a tree, because once we have a tree, we just go through the tree, traverse it, and at the end, when we reach a leaf node, so this is a leaf node, this is a leaf node, this is also a leaf node, and the leaf nodes represent the final predictions. And these nodes are not leaf nodes; these are parent nodes. Anything that has children will not be a leaf node. So that's. However, learning a tree. So the idea is, how do we build this tree? That is non-trivial, and that's what we're going to cover over the next couple lectures. How do we learn it? It's actually non-trivial. But if we do have it, you see, it's very nice. We can do predictions very easily, and it's also interpretable. We can understand what it's doing, what this classifier is doing. It's just checking the color and then the shape. It's very interpretable. So what the decision tree does is that they basically build a series of boundaries in the feature space. So here, imagine if you have these features x and y, and we have these regions are pluses, these are pluses, it's also plus, these are minus, minus, minus. And it's building a series of boundaries. It's fragmenting the feature space by asking a series of questions. So if x is more than 3, that means this is our boundary, and then we're splitting on this side. And then if y is greater than 7, so here, this line here, then it means we're above. So then we basically at this plus. Otherwise, we're at these minuses. And the same. And we keep asking a series of questions, and we partition. By asking these questions, we literally partition the feature space, and we divide it. And of course, it helps us very easily visualize. Once we can visualize either by partitioning the space or by having the tree. But in particular, the tree sometimes can be even easier to visualize the complexity of the learned model, rather than you looking at these boundaries and looking at how the model learns. Because the model is learning essentially these boundaries. But sometimes it might be easier to judge the complexity from this, because, for example, from the tree we can look at the depth of the tree, like what is the depth of the tree, or to understand how many questions we have to ask until we reach a solution, or even the width of the tree. How complex are these queries? Like, is this a query simple to evaluate or much more complex to evaluate, and so on. Yeah. So they can represent any Boolean function, these decision trees. They can represent any Boolean function and can be viewed as a way to compress, to provide a compact representation of the data. It can be seen as a form of compression. And for a given data, there's actually many types of trees that are possible. So for the same data set, there's many ways. For example, we can flip these around. For example, we can ask questions in different order, and we'll see very shortly what's the implications of doing that. But learning a good tree from the data is not easy. It can be challenging. So if we have, let's do this quick, simple example. So do I play tennis today or not? So we have an example. We have to decide if we're going to play tennis. We have 4 features: outlook, if it's sun, overcast or rain, temperature, hot, mild, cold, humidity, high, normal, low, and wind. And we also have labels, and the binary labels are the classification. Yes, I will play tennis, or no, I will not play tennis, based on these 4. So we can get, this is our data set, for example. So O means outlook, which can be sunny, overcast or rain. T, again, temperature, hot, medium, cold. Humidity, high, normal, low. And this is a wind, strong or weak. And so this will be our data set. So we took measurements for 2 weeks here. So for every day, I decided, so on the first day I don't play tennis, I don't play tennis, then I play on the third day, and we took these observations for over 2 weeks. And we want to build a tree. So how do you start? So generally we pick a feature, so let's say outlook, and then we split on it. So if the outlook is overcast, for example, we always put a plus. And the reason why is because if you look at all the overcast examples, this is a plus. This number 7 is also a plus, and 12 and 13 are also pluses. So basically, every time the outlook was overcast, we play tennis. So then we just say this is overcast, and we do the same with the other ones. If it's sunny, we realize sometimes we have minuses, and sometimes we have pluses, like here. So we have to ask more questions, and we keep doing this until we learn a tree. Any questions? Yeah.
What if we have 2 rows that are identical but have different outcomes?
2 rows that are identical but have different outcomes. Yes. We'll see. I won't answer yet. We'll see in the next lecture. Yeah.
Would it just be like an outlier
Yeah, exactly. That's one solution. Yeah. We'll see next lecture. For now, we're assuming we don't have these contradictory examples. Yeah. So trying to think. So how much time do we still have? 10 minutes. I have a quiz. Shall we do a short quiz? I have prepared a quiz, and or shall we continue this? Okay. Quiz? Okay. Yeah. Okay. So let's stop here. We'll continue next time, and we'll do a short quiz. So let's join quickly. So use this link, joinmyquiz.com, and this is the code. Everyone connected? Who's still not connected? Are we still waiting for someone? Okay. So here. So joinmyquiz.com and then put this code. So just go to this website and enter that code. Yeah. Okay. Everyone in? All right. So let's start. 3, 2, 1. Based on the example figure, what is the effect of changing the value of k in k nearest neighbors? So what is happening once we change the value of k? I won't wait for all 2 minutes. I should have given us smaller time. Let's take another 30 seconds and we'll look at it. Okay, I'll finish in 5, 4, 3. A few more answers, okay? Okay. They're coming. Okay. I'll finish soon. So, end question. Let's see what we have. The edges become smoother. Yes. So as you increase k, the edges, the boundaries become smoother The boundaries become more smooth. Segmentation is more uniform around data points. Yes. Oops. I cannot scroll this. A much more smooth decision boundary. Yeah. The boundaries for the red, green, and blue are more defined. Decision boundaries change. The distinction area getting more bigger. I don't know what that means. But yes, this is good. These are good. So next question. I should launch it from here. Yeah. So next question. So we have multiple decision trees that solve a given problem. What characteristics do we want? And again, let's stay a minute here. I forgot to change the default timers. Okay, 15 more seconds. And we'll look. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, let's see. We want a tree with the shortest possible height. Yes. So the height will give us how many, on average, how many questions do we have to ask until we reach a solution. So that's important. So having a shorter height means we can get our solution faster. The tree should be as small as possible. Yes. So of course, smaller trees are better. Best root and minimal depth. Yes, minimal depth. So height. Yes. What do you mean by best root? So the root node, what do you mean by the best root?
The best first decision to make that makes them.
Yeah.
Enforces the minimal depth.
Yeah. That makes sense. We'll see very soon in the next lecture how we do that. And not only at the root node, but at every node. How do we make the best decision?
You don't want to start with the most independent features, right?
Yeah. We'll see very soon. We'll see very soon. Shortest average length from root to leaves. Yes, that's the height of the tree. It's easy to compute the queries. Basically, inference speed. Yeah. Yes, we want a fast inference. So with the best accuracy. Whichever is the smallest decision tree. Yeah. Choose a tree that best splits the data. This is very interesting. So this is an answer that focuses on which tree finds the best boundaries. Not the actual properties of the tree. So that's also important, of course. We want to have good and robust boundaries. Yes. More accurate, less complex. Number of boundaries should be minimum. What's the number of boundaries? What's in the tree, in terms of the tree? What is that equivalent with? Yeah. Queries. Yes. How many queries you make? Each boundary is a query you make in the leaf. The question you ask is x bigger than 5. Am I hungry now? Or do we have $50? Yes. Choose. Okay. So in particular, we'll see next lecture, and we're finishing here. Well, we'll see very shortly in the next lecture how we can have multiple trees, for example. So these will be two trees that answer exactly the same, but one of them, for example, one of them is more preferred than the other because the query time is shorter also. So for example, you see how we will see very shortly how we can compare these kind of trees in a bit more detailed way. Okay, so I'll see you in the next lecture on Thursday.
Do you have a minute to talk after class?
Yeah.
Okay.
Yeah.
I had a question about